following is a demonstration of Western Services Corporation 3-Key Master simulation technology in an SAE, or Simulation Assisted Engineering application. Through the use of the advanced object-oriented modeling tools, which are an integral part of the simulation system, this simple demonstration will illustrate how plant design and optimization can be accomplished. Here we have a simplified hydraulic system which, through first principles modeling, dynamically calculates pressure, temperature, flow, and all of the relevant parameters associated with the system. You may think of it as a redundant train lube oil system for a nuclear power plant turbine, for example. The system includes a tank, pumps, valves, accumulator, and other objects with dynamic indication of status and visualization of analog parameters through tables and trends. To support the hydraulic system dynamics, elements of logic and control, transmitters, and I/O, for example switches, lamps, and push buttons, are included. We start by demonstrating an initial design concept. When we stop the running pump, we'll see the pressure in the header degrade as the pump coasts down. The logic and control will cause the standby pump to auto-start on a low-pressure alarm condition, represented by the white line on the trend, after an applicable time delay, in this case 9 seconds. As we have seen, the standby pump auto-started correctly, but not in time to prevent a trip, represented by the red line on the trend and audible alarm. Now we will test possible changes in the design and how they will impact and possibly improve the design. But first, we'll restart the first pump. You'll note that with both pumps running, the overpressure alarm, represented by the yellow line on the trend, will sound, though we will need to reset the latch or RS flip-flop to stop the standby and rearm the auto-start logic. Next, we'll change the design by shortening the time delay of the auto-start of the standby pump from 9 seconds to 3 seconds. Now, we can repeat the first exercise and observe the result. Indeed, this time we'll see that we did not reach the trip set point. With Master's integrated tools and plant design capability, we can do so much more. Now, we will again reset the system, restarting the first pump and stopping and rearming the standby. Next, we will observe the effect of reducing the size of the accumulator in the system, effectively reducing the overall capacity. This could be due to design considerations, either of cost or simply of having only a certain volume or space in which to fit the accumulator. Now, with the system reset and stabilized, and only this change in here, run the scenario again, stopping the running pump, and now we'll see that we no longer meet design criteria because the pressure degrades much faster, as we expect. Several possible design changes may be made to mitigate this problem. For this example, after we reset the system again, we'll replace the current pump, the standby unit, with a much faster acting unit, shown here in a simplified way by putting a smaller inertia factor. Running the same scenario again now results in a system which survives and does not trip, but perhaps comes too close to our safety margin. We can now, for example, reevaluate our control system. Here, we will raise the low pressure set point from 5 bar to 6 bar, and we can reduce the time delay from 3 seconds to 2 seconds. After resetting the system one last time, we'll run the scenario one more time, and we can note that we've gained some significant safety margin to prevent a potential trip. Keeping in mind that this is a very simplified example to illustrate potential SAE application on an actual plant design use, every element of the system can be manipulated within the possible constraints of what is available for the designer to optimize the system. For example, a library of possible available pumps with actual characteristics can be included in the simulation and quickly changed out to see the effects of each. Different valves can be considered, as well as lengths, diameters, and other characteristics of all piping. And of course, logic can be designed in different ways to realize the optimum design to control the selected equipment. There are no practical limitations to what can be accomplished using the 3KeyMaster simulation system and modeling tools. This concludes the 3KeyMaster Simulation Assisted Engineering demonstration.